Okay, so after having looked at all the characteristic of a BJT, right? So what we want to do now is to try to solve and analyze a circuit where we implement a transistor in it. So let's say the question is to compute the parameters of the circuit by assuming that the gain beta in CE. So in CE, as we've seen just now, CE means common emitters. Assume that the gain beta is equal to 100, right? So when it says compute the parameters, so what does it mean by parameters? Parameters mean calculate the voltages across the junction in the across the transistors. So usually when we ask for that, the voltage that we want to measure is the voltage across the junction C and E, this VCE, right? This VCE. So we want to measure this VCE, right? So this VCE. So where is VCE? VCE is basically, if I put an arrow to show the difference potential of VCE, is actually it's VC minus VE, right? So it's the voltage at this point minus the voltage at this point. So that's what we call VCE. In order to be able to measure VCE, what we need is to solve the other parameters before that, right? So we'll see in this exercise how do we do that. So before that, if we have a question that looks like this, what happens is sometimes it might be confusing, right? So the thing that we can do is to redraw it into a circuit that represents better the components around the transistors. For example, here there is a point where we have a potential difference at this point. Voltage at this point is at 12 volts. What does it mean to have a voltage measured at a point? It means basically is the voltage between this point and a mass. So between this point and a mass, the voltage is 12 volt. And if the voltage is applied across the at the point of the collector, usually we will call it as VCC. For the voltage that is applied here at the junction of the base, so here is the base C, here is the collector, here is the emitter. Voltage at point B, a branch that leading to point B, usually we call it as VBB. So it's just in terms of notation. And the voltage that is can be measured at the point of E, this voltage is if there is a voltage, we would call it as VEE, but there's no voltage over here applied, right? So that's why here when we transform it into this circuit, we can see that we have this voltage applied. So it is basically a power supply. So we have VBB at B, at C we have VCC, right? And then the parameters that we are interested in that are gonna help us, there's another parameter which is VBE, because if you remember the characteristic, there are 3 points in the characteristics that we want to apply. The first one is to know that if it is turned on, the transistor is turned on, then VBE will be equal to 0.7 volts. So we will check later if it is turned on or turned off. If it is turned on, then we will consider that VB equals to 0.7 volts. And another point is that if it is turned on, it means the transistor would have a gain. In CE, the gain is beta. And what is beta? Beta is basically the ratio between IC and IB. Beta is IC over IB. So where is IC? IC is here, the current that get into the collectors, and IB is the current that excite the base of the transistors. And then finally, the other thing that we learn in the characteristic as well is if we apply a KCL over here, we can see that in CE we have the current that comes out from the junction of the emitter equals to IB plus IC. So these 3 characteristics that we have learned previously is the one that we're going to be using to solve the exercise in order to find, for example, to find VCE. The question is, when we ask for parameters, is to find what is VC, what is VCE. So let's have a look. So here the question is over here now. The thing that we can do is the first thing that we need to do is basically to check whether our transistor is in on mode or in off mode. So to do so, basically we have first one is to check if our BJT is on. So to do so, we assume that the BJT is in cut-off mode. What does it mean to be in cut-off mode? When it is in cut-off mode, it means that we have no current at the base. Therefore, we will not have current at the emitter and the collector. What is the consequence of not having IB, IE, and IC? So to know the consequence, what we need to do is we need to look at the to do some calculation across the circuit. So there are two KVL that we can see where we can write equations. The first one is KVL around BE. So BE is basically from base to emitter. There is this one KVL, and then the second one is around CE. CE is basically between this point and this point, right? So if we look at BE, the KVL in BE, what is the KVL? We have KVL in BE is we have VBB, right? VBB, so the current IB goes into this direction, so we have, I would call this as VRB, because this resistance usually called as RB, the resistance at the base. And then what else do we have in this loop 1? We also have VBE, and then we would have VRE, because the resistance we would call it as RE, resistance across the emitter. So that's where we get, if we look into the equation, so VBB is this 4 volts. VRB, what is VRB? VRB is basically this 40 kilo ohm, RB, which is RB, multiplied by IB, right? That is just Ohm law, RB multiplied by IB, plus here VBE, and then plus VRE over here. So we complete the loop now, starting from the ground back to the ground. So VRE, what is VRE? Again, VRE is just RE multiplied by IE, by Ohm law. So RE is 1 kilo, 10 to the power 3. Here we can see RE. So that's our first KVL. In second KVL, let's verify. So we will have the 12 volts. If we go here, so we have 12 volts equals to, so we have VRC. So what is VRC? It's RC multiplied by IC. So RC is 1 kilo multiplied by IC, plus then we have VCE, plus VCE, and then plus, so this, what is this? 1 kilo times IE. 1 kilo times IE is basically VRE. So this is VRE. It's RE multiplied by IE, right? So we have these two KVL. This is the first KVL. This is the second KVL. So how would we use this? We're back to checking the BJT if it is on or off. We said just now if it is off, then IB equals to 0, IE equals to 0, and IC equals to 0. Let's plug in the value of IB, IE, and IC equals to 0 into the KVL1, BE KVL. KVL where we have the junction BE. So if we plug in, so the equation that we get from here, it is this equation. If we plug in, for example, IB equals to 0, IE equals to 0, then that would mean that at the end we will have 4 equals to, so 40 times 0, we have 0. Here is 0, 4 equals to VBE. So we found out that VBE equals to 4. And when VBE equals to 4, we know that 4 is larger than, it is basically larger than the bias voltage. If it is larger than the bias voltage, it means it is turned on. It is basically on, and it is not off, right? It is not off. So that's how we verify whether it's turned on or turned off. Once we verify that, then it means we can take into consideration that VBE is, we can use the properties, the characteristic that VBE equals to 0.7 volts. and we'll have IB larger than 0, which we don't know what's the value yet, that we have to find later. So in next slide we'll see how do we find it. So just now in previous slide we have checked if basically the transistor is on or off. So we have concluded that the transistor is on. So what's the consequence of it being on? The consequence of being on is that all the characteristic that we have seen previously is applied. So the characteristic is, the first one is we know that VBE equals to 0.7. So we consider that we have a semiconductor of silicon. And then the question also says that we would have beta equals to 100. So what is beta? Beta is the gain coefficient, where we have IC equals to beta IB, right? So that's the second characteristic that we're going to use. And then the other characteristic that we can use as well is the KCL in the transistor, in the junction of transistor, which says that IE equals to IC plus IB. So let's look at this first. We know that IC equals to beta IB, so we can replace basically IC in here. It gives us an expression of IE that only depends on IB. So now IE becomes, so IC is beta IB, right? So IC is beta IB. We have beta IB plus IB. So we can simplify the writing of IE into just basically it's beta plus 1 multiplied by IB. Now we can get rid of IE, or if we have IE, we can write it in terms of IB. So let's look back at the KVL that we had. So the KVL, there was one in this loop and another one in this loop, right? So basically we also have a ground here, 12 volt here. We call this as VCC. We call this as VBB, sorry. So the first KVL was VBB equals to, so VRB which is RB multiplied by IB, plus VBE, and then plus VRE which is RE multiplied by IE. So the first remark that you can see that is now knowing that we apply the characteristic that we've seen here because we have the transistors on. Now we know the value of VBE, which is 0.7 volts. VBB, we know the value, it is 4 volts. RB, we also know the value, so RB is the resistance over here, it is 1 kilo. IB is the thing that we don't know yet, so it's a parameter that we want to look for. RE, so RE is this, RE is also 1 kilo ohm. And then IE is something that we don't know, right? It's also something that we don't know. So this equation has two unknowns, IE and IB. But if you look at here, IE can be written as a function of IB as well. So we can write VBB is also equals to RB IB plus VBE plus RE multiplied by, so we've deduced that previously IE is beta plus 1 IB. So now having this, we see that this equation, the only unknown is IB. IB, this is the only unknown. We know all other parameters, we know it. So from here what happened is we can calculate IB. So I'll let you do the rearrangement of the equation, but at the end what you will find is that you'll find that IB equals to 54 microamperes. So IB equals to 54 microamperes. If we have IB equals to 54 microamperes, it means that we can also calculate IC, which is equal to beta IB. So it's 100 times 54 microamperes. So now we have two things, IB and IC. So knowing IB and IC, what we can know next is basically IE, right? So therefore we have IE, which is equals to IE is IB plus IC. So IB is 54 microamps, and then plus, so basically 54 multiplied by 100, we would have, I'll just write 5400 microamps. So I'm just going to leave it like this for a moment. So now we know all the parameters of IB, IC and IE. So what's the other thing that we don't know? The other thing that we would like to know is basically it's VCE. So where do we find VCE? It's in the second loop, in this one. So in second loop, we can write, what we can write is VCC, so VCC is this 12 volt, equals to VRC, so this is VRC, voltage across RC, is RC multiplied by IC, plus VCE, so is the parameter that we're looking for, that we don't know. IC, now we have found it here, right, or here to be exact. So RC known parameter, IC known parameter, plus VCE, and the other one is basically it's VRE. So VRE is this voltage, it's RE multiplied by IE, and again RA is a known parameter, it's 1 kilo ohm, and IE has been found here. So now VCC we also know is equals to 12 volt. Now we can deduce VCE easily, which is VCE equals to VCC minus RC IC minus RE IE. So I'll let you replace the value. So VCC is 12 volts, RC is 1 kilo ohm, IC is the value that I found previously, so it's 5400 microamps, RE is also 1 kilo, and IE is this value. IE is 54 microamps plus 5400 microamps. So if we do the calculation, then we'll find VCE. So that's all what you need to do. Find the parameters, mean find what's the value of IB, IC, IE and VCE, right? That's what we want. And the steps involved are all the steps that have been shown here. So it's not complicated, it's just to basically to apply all the knowledge, all the prior knowledge that you have previously, KVL, KCL, and then just applying the characteristic, the condition of utilization of a transistor. Alright. So now here we have another example. So it's example number 2. This might seem more complicated, but there's nothing complicated in here. It's the same thing. So you give a parameter of beta equals to 150, VBE equals to 0.7. So it assumes that the transistor is on, so you don't have to do the checking anymore. And it asks you to find V0. Where is V0? V0 is the voltage that's shown here. V0 is basically VCE, because this is the collector terminal, this is the emitter terminal, and this is the base terminal, right? So again, in order to do so, we have basically to calculate VCE, we need to write the KVL in this loop tree. And in this loop tree, we will be needing VRC. So this is, I will call this as RC, and we will be needing also VRE. So we need IE, and then we need IC. So again, we come back to the same conclusion. What we need to calculate is basically IC, IE, and in order to calculate IC and IE, we will use beta, and we will need before that IB. So the key to it is to start first with finding IB. What is IB? If you find IB, then you'll be able to find IC, because IC is just beta IB, and then you will also be able to find IE, because IE is just IC plus IB. So what is IB? And once you have find IC and IE, you can just replace it in VRC using Ohm law, in VRE using Ohm law, and you can write the the KVL inside loop 3 and you'll find VC. That's easy. So the one thing that we need to find is what IB. What is IB? So how would you tackle this? Now if we look into this structure, we can remark that there is basically a voltage divider. So again, it's a usage of prior knowledge that you've learned in previous chapter, right? So voltage divider. So where is the voltage divider? If I have to redraw, we have the supply voltage equals to A. So A should be, of course, should be given. And then we have, I will call this 100 kilo ohm as R1, but I'm drawing it now in a different way, but it's still the same thing. So I have R1, and then after R1, basically I have a junction, right? And then here underneath I have R2, and here we have mass, right? And this is, I will call this as VR2, voltage across resistance 2, and here you have VR1, voltage across resistance 1. And then where is IB? IB is the current that goes out here. Here we have, I would call it as I1, it is called as I1. And then here we have I, is called as I2. So how do you find IB? To find IB, it's easy. If we look at this node, we can write a KCL at this node. I'll call the node as node star. So KCL in node star, on node star is, what is the KCL? So the sum of entering current equals to the sum of leaving current. So it's I1 equals to I2 plus IB. So it means if you can find I1 and I2, you'll be able to find IB. And if you can find IB, you can solve the whole exercise. So how do you find I1? So I1 is the current that goes across R1. I1 is, of course, if we write the Ohm law, if I call the voltage across R1 as R1, I1 is VR1 over R1, right? It's over here. It's VR1 over R1, and I2 is it is the same thing, but now it's VR2 over R2, right? It's VR2 over R2. So the question now is, what is VR2 and what is VR1? So now we will use the properties of voltage divider. VR2 is basically a portion of the voltage of A. If you want to calculate VR2, voltage divider say that VR2 is equals to A, the whole voltage, multiplies by the resistance R2 over the sum of resistance across the junction, which is R1 plus R2. So that's VR2. We found out VR2. That's easy. Next, what is VR1? If I can find VR1, that means that in this loop, if I write the KVL, I'll find that A minus VR1 minus VR2 equals to 0. That means I can find VR1 equals to A minus VR2. We found VR2 over here, and A is something, a value that's given, so I will know the value of VR2. Now, knowing the value of VR1 and VR2, I can therefore calculate I1 and I2. And then I'll find IB, which is I2 minus I1. Once you have found IB, go back here, we calculate IC, calculate IE, and then once you have IC, IE and IB, we can go calculate write the KVL in loop 3 and find VC. So I'll let you finish this part, right? So that's basically what we do in transistors. Just use the same properties, and then just play around and try to figure out how to find IB, because this is basically the most important parameters. It's the current that actuate or switch on the transistor, and if you found IB, then the rest you will find it. right? So that's all about the exercise, and now we will look at another example of configuration of transistor that might be interesting to use. So the another configuration of transistor that is interesting to use is what we call the Darlington transistor, right? So what is Darlington transistor? Darlington transistor is basically just an arrangement of two standard transistor, either NPN or PNP, which are put one after the other. So why do we do this? We do this basically is to achieve two things. The first one is to get a more sensitive transistor and a larger current gain. So for example, if we have a typical value of beta of the gain, it is ranging from 50 to 200. If it is insufficient, then we might want to increase the beta. So how do we increase the beta? Is by putting basically two transistors in this configuration, one after the other. Of course, it will be the same type, NPN or PNP. So the method is to put the emitter current of the first transistor, TR1, so the emitter current of the first transistor, we make it we use it as the base current for the second transistor. So TR1 is connected basically TR1 is connected as an emitter follower and TR2 as a common emitter amplifier. And what is the new gain? The new gain is basically just the product of the two gain of the transistor. So imagine if you have the gain of the first transistor at 50 and the second is also at 50, then the new gain is 50 multiplied by 50. Now we have a larger gain at 200 and 250. So this is the Darlington transistor. So this is the configuration if using two NPN side by side. This is when we use PNP side by side. So it's the same thing. The new beta, which we call beta Darlington, is the product of the two beta, the first transistor and the second transistor, right? And the new VBE, if you consider the totality, the assembly of the Darlington transistor, the VBE, the total VBE will be equals to VBE1 plus VBE2, right? So if they are the same transistor, which it will be equivalent or closely equivalent to 2 VBE1. Well, it depends basically on the precision of the measurement on the transistor. If the beta are really equals, then this can be applied. So little words on the advantages and disadvantages of Darlington transistor. We by using it, the advantages are we will be able to obtain a very high current gain. Beta is 2 times the beta. We will have a very high input impedance for overall circuit. Darlington pairs are widely available in a single package. They are available in single package, which are already arranged in that manner, and they are convenient and easy circuit configuration to use. The problem is that we have a slow switching speed. So switching speed is not something that we have discussed here. Switching speed is basically if IB is not just one shot switching on. Basically, usually for example in an inverter, it use the input is basically coming from a pulse width modulation signal. If the frequency of that PWM is very high, then there might be a problem because basically each transistor has a switching time, which we call slew rate. And well, this is not discussed here, but there is something that is very important if we want to go further in the study of power electronics. And then we have, therefore, if the switching speed is low, then we have a limited bandwidth, and it can also introduce a phase shift. Phase shift means it introduce a lag between the input and output that can give problems at certain frequencies. The another disadvantage is to have higher overall base emitter voltage, which previously was 0.7, but now we will need more than 0.7 to turn it on. And then finally we will have also high saturation voltages, which can lead to high levels of power dissipation in some applications. I mean, we will create a lot more losses. So there are of course other type of usage and configuration of transistors. There are also other type of transistors other than BJT. There are FET transistors, but just for a chapter of introduction in this electrical and electronic technology course, this is what I think the most important thing that we need to look at, that introduce you to the basic of a transistor. Of course, for further knowledge, you can always look into more references on other types of transistors and other configuration of BJT as well. So that's all for transistor, and see you in the next chapter.